Welcome back, computer vision enthusiasts. Today we're diving into the fascinating world of convolutional neural networks, or CNNs, the technology behind facial recognition, self-driving cars, and so much more. To understand why CNNs are so special, let's first consider the limitations of regular neural networks. Imagine trying to recognize a cat in a photo. A standard neural network would need to process every pixel individually, resulting in millions of connections. Worse yet, if the cat moves even slightly, the network might see it as a completely different image. This is inefficient and not robust. CNNs solve these problems by focusing on local patterns and relationships between nearby pixels, making them much smarter and more adaptable for visual tasks. Let's see how they do it. What makes CNNs so effective at interpreting images? The core idea is feature detection. CNNs are designed to automatically learn spatial hierarchies of features from images. They use local connectivity, meaning each neuron only looks at a small region of the input, and parameter sharing, where the same weights are used across different positions. This allows CNNs to detect patterns anywhere in the image, a property known as spatial invariant. Think of it like recognizing a face. You first notice edges, then shapes like eyes and nose, and finally the whole face. CNNs mimic this process through layers of increasing complexity. The magic happens in the convolution operation, where a filter slides across the image, searching for specific patterns. This is how CNNs build up their understanding step by step. Let's break down the main building blocks of a CNN. First, convolutional layers act as feature detectors, applying filters to the input image to create feature maps that highlight where certain patterns occur. Next, pooling layers downsample these feature maps, reducing the amount of data and helping the network focus on the most important features. This not only makes computation more efficient but also provides some translation invariance, so the network can recognize objects even if they move slightly. After several convolution and pooling layers, fully connected layers combine all the learned features to make the final classification. Activation functions like ReLU introduce nonlinearity, enabling the network to learn complex patterns. Together, these components allow CNNs to transform raw pixels into meaningful insights. Now let's see how convolution and pooling actually work. In convolution, a small filter or kernel, often 3x3 or 5x5, slides across the image. At each position, it performs a dot product with the underlying pixels, producing a feature map that highlights where specific patterns like edges are found. For example, an edge detection filter will light up areas where pixel values change rapidly, outlining the shapes in the image. Pooling comes next, typically using max pooling, which takes the maximum value from each region of the feature map. This reduces the spatial size, decreases computational requirements, and preserves the most important information. Together, these operations allow CNNs to efficiently learn and recognize complex visual features, no matter where they appear in the image. Let's walk through a complete CNN architecture example. We start with an input image, such as a 224x224 color photo. The first convolutional block applies filters to detect simple features like edges and colors, followed by a pooling layer to reduce size. The next blocks use more filters to find increasingly complex patterns and object parts. After several rounds, the network flattens the data and passes it through fully connected layers, which combine all the learned features to make a final prediction, like identifying a cat or a car. Early layers focus on basic details, middle layers on patterns and parts, and late layers on whole objects. This hierarchical approach is what makes CNNs so powerful for visual recognition. Over the years, several CNN architectures have shaped the field. LeNet-5 was a pioneer for digit recognition, while AlexNet revolutionized computer vision by winning the ImageNet competition. VGGNet showed the power of deep networks, and RaiseNet introduced residual connections, allowing for extremely deep models. Modern architectures like EfficientNet and vision transformers continue to push boundaries. Training CNNs involves techniques like data augmentation, creating variations of training images to improve generalization, and transfer learning, where pre-trained networks are fine-tuned for new tasks. Despite their power, CNNs face challenges like overfitting, high computational demands, and the need for careful tuning. Still, their impact on AI is undeniable. CNNs have transformed countless industries. In facial recognition, they power phone unlocking and social media tagging. In healthcare, they assist doctors by detecting tumors in X-rays and MRIs. Autonomous vehicles rely on CNNs for object and lane detection, making self-driving cars possible. Manufacturing uses CNNs for quality control, sorting products, and spotting defects. In entertainment, they enable photo organization, augmented reality filters, and video analysis. Even agriculture benefits, with CNNs monitoring crop health and predicting yields. The beauty of CNNs lies in their ability to mimic how our own visual cortex processes information, making machines capable of understanding the world through images.